we know that we can find the average rate of change using the formula m equals f of b minus f of a over b minus a. And for example, let's say we are on a train. That train is slowing down, but that train was going pretty fast. It was going 150 miles per hour. And it's slowing down at the rate of, at the function, using the function f of t is equal to negative 16t squared plus 150. And so this is an upside down parabola. When we plug in t equals 0, we're at exactly 150, and as we go forward, we are tending towards a speed of 0. And we might want to know our average speed between 2 points. For example, let's say we want to know our average speed between times 0 and 2. Well, in fact, let's go up to our average speed between times 2 and 3. Let's say we are looking for our average speed between 2 and 3. We can do this in a really simple way. We can use our average rate of change formula, and we can just plug in 2 and 3. F of 3 is equal to negative 16 times 3 squared is 9 plus 150. F of 2 is equal to negative 16, 2 squared is 4 times 4 plus 150. In the top case, we're going to get 6 at the end. Negative 16 times 9 is 144. And f of 2, negative 16 times 4 is going to be 64. 150 minus 64 is going to be exactly 86. And so we have f of b, which is 6, minus f of a, which is 86, over b minus a, which is 3 minus 2, which gives us negative 80. So we have negative 80 here. And given negative 80, that's our average rate of change between points 2 and 3. So let's say that this is at point 2. Let's say this is at point 3. That's telling us the slope of this line here. But what if we wanted something more specific? What if I wanted the instantaneous acceleration at, say, the point 2? Well, we have the average rate of change. If we want the instantaneous rate of change, we might do something like this. We might look at the interval 2, 2.1. And if I look at 2.1, I get, you don't have to do this math unless you have a calculator at hand, but 2.1 minus f of 2 over 2.1 minus 2, which gives me 79.44 minus 86 over 0.1, which is about negative 65.6. If I wanted something even closer to just 2, I might look at the interval 2, 2.01, and you might see where I'm going with this. If I look at this interval, I get f of 2.01 minus f of 2 over 2.01 minus 2 is equal to 85.3584 minus 86 over 0.01, which gives me 64.16. And if I keep going and I keep going, we see that we're approaching negative 64 for our speed. We see that we're, for our acceleration, we see that we're approaching negative 64. And so what we see here is we can take our average rate of change and we can get arbitrarily close. We can bring B and A together arbitrarily close to figure out our instantaneous rate of change. And that specifically, that process, we can define using limits, which is what we defined in the past. So we have a couple definitions here. Let's start with the tangent line of a function is the line that touches the function at one specific point and what it does for us is it approximates that function. At that point. So, if we go back to our previous example, we have, I'll draw a big graph this time, we had a parabola describing a train slowing down. And we looked between 2 points, which means we touched the function at exactly those 2 points. We drew the line that touched the function at those 2 points, and we found the slope of that line. Well, if I bring this second point a little bit closer, we see that we're going to get this blue line, which is a little bit closer to the slope at point A. It's a little bit closer to the slope at this top point. If I bring it a little bit closer, say to here, we get a really good approximation. And if I bring it all the way, if I bring it arbitrarily close, if I make the 2 points pretty much equal to each other, what I get is a point that touches this function at only one spot, and it's at the spot of interest, which means I can find the slope at that point, despite the fact that this function has a continuously changing slope. And we actually have a way of bringing things arbitrarily close together now, and that way is limits. So we have another definition. The instantaneous rate of change of a function f at x equals a is the slope of the tangent line passing through the point a f of a. And if it exists, it is given by m is equal to f of x minus f of a over x minus a. So this is the same slope formula, but we're going to add a piece. We want x and a to get arbitrarily close together. And the way we described that in the past is we had the limit as x approaches a. So x is going to get arbitrarily close to a. X can never equal a, because if x were to equal a, we would have a divide by 0 problem. But we can say the limit as x gets closer and closer to a of f of x minus f of a over x minus a is the instantaneous rate of change. And we're going to use that formula a lot in this class.